Okay, hello Nidir. This is the second portion of ideal gases. So we'll continue from here. Uh, there's topic left, which is um, kinetic model. So this model will be about connecting, as we talked about in the last one, the microscopic to the macroscopic. So macroscopic, as we said last time, were PVT, pressure, volume, temperature, and microscopic are like velocities of the individual particle, the kinetic energies of the individual particles, the forces between individual particles, and stuff like that. And this kinetic model essentially acts as like a bridge between those two, right? So the idea is, what is this kinetic model and what do we understand of this? So kinetic model says that gas is made of small particles with no uh, force of attraction between them, uh, which are moving at fast speed, uh, moving like hard spheres. So this is the important part, that they are like hard concrete balls, like big balls, which are like metal balls maybe, and they keep bouncing around each other, right? And because so this is the same model as we talk about every time, that the particles in a box model, and things just keep moving, and then there's so many, and we last time we saw that they're moving at us almost an amazing speed of 400 meters per second, which translates to over 1,000 kilometers per hour, right? So all of these things keep moving very fast, and they are like hard spheres. So the idea is, this hard sphere can bounce on either another hard sphere, so that's what we can call a collision internal to the gas, or we can say that it also can collide to the wall. uh, in that case, the wall will feel certain pressure, right? So now we start to, like, once we start to understand it as, oh, hard spheres moving very fast, um, we can start to explain certain things. So let's see what all we can explain here. So your book gives you a table, like without even doing calculation we can say something about a few things. So let's see. So let's see the first point here. It says gas contains large number of particles moving at random to collide elastically with the walls and with each other. So with the walls and with each other, right? So this is the assumption. So the idea is that kinetic energy can't be lost, right? So if two things are colliding, they can like maybe change their velocities in such a way that the energy remains same. So even when it is colliding to the wall, its kinetic energy will remain same. So in such a case, so it's starting from here, coming here, collides the wall, and then comes back here. So it's minus v velocity initially and then plus v. In both the cases, half mv square is same, because minus v and plus v whole square is the same, right? So kinetic energy remains unchanged. But what has happened is, this wall has started to feel a force, because it has to kind of rebound, right? So if something is hitting it, it will feel a force. So that's what is being said here, that kinetic energy cannot be lost. Uh, and so we can also explain what we talked about in thermodynamics. This internal energy U term is, U is basically the sum of all the kinetic energies of all the particles. Now, right? So because we don't have any intermolecular forces, so there is no potential energy term, because there is no forces. But everything is moving, so everything has a kinetic energy, and that kinetic energy kind of remains constant if at a particular temperature. And you will see that if it increase temperature, then that term can get increased. Okay. So then the second part, they are saying the forces between the particles are negligible except during collision. So this is the attraction forces between two particles. So we saw that in gravitation, if you keep two particles, then they have an attractive force, which is gmm by r. Or if you keep two charges plus or minus, you will see in the next chapter that it is k q1 q2 by r. So these are all forces that act like as a non-contact force, like they act as from a distance. So these are force of attraction or force of repulsion between two particles, right? We say that no such forces are present. We just say that these are freely moving particles who are just colliding with each other. So that's what they mean by forces between the particles are negligible except during collisions. Uh, so another explanation for that they are saying is if they had attraction force between each other, then they would clump together in the middle. All of these things would come in the middle of the container, right? Like all of these things would come in the middle of the container, right? And so you would, but that's not the case. We don't see that that they are in the middle. Okay, let's read the third point. It says volume of the particle is negligible as compared to the volume of the gas, right? So the volumes of these all spheres and the volume that it occupies in this container is very different. So an explanation for that they give is if you keep a liquid here, right? And this liquid, like say 100 ml of liquid, can evaporate and form steam in the whole area, right? So that would tell you that the same thing is kind of going, the same amount of particles are kind of spreading into a larger volume, which is why the volume of particles might only be this much, but it can spread through the whole area, right? Okay, and the last one they're saying is the time of collision of by a particle with the container walls is negligible compared to the time between collisions. So this particle is coming, so this particle has just struck the wall, and then this is coming, and then this will have to travel till here to meet the next particle. So the time between from one collision to the other is very big, but time for a collision, it's like how a ball bounces on a piece of ground. The time that the ball is in contact with the ground is very small. In that small time, a great deal of force is transferred. Right, so okay, we can make these are fairly reasonable things. They can you can all explain them once you think about hard shells, hard spheres kind of going around, right? So now let's try to do some like the kinetic model, which we call. So let's try to do some calculation with it. So we'll start with one particle. So imagine that there is a box like this, right? So this is a box, and there's one particle that's kind of going towards the wall. It hits this wall, it kind of comes back and then hits this wall and then goes back and then hits this wall again, right? So this is our model. So this is one particle of mass m that's doing that, and I am interested in knowing how what is the amount of force or pressure exerted on this wall only. So this will say wall 1, and I want to know what is the pressure on wall 1. So okay, maybe I can start writing a few things. Maybe if I assume that the velocity is v here, uh, then the backward velocity when it comes back is minus v, right? So I can find change of momentum here. Change of momentum. So change of momentum is final momentum, which is m into minus v, uh, minus initial momentum. Initial momentum is m into v, right? So this becomes change in momentum is minus 2mv. Okay, so we can say that this wall has changed the momentum this much. Okay, then we can say force. What's the force exerted by this wall on the particle to change this momentum? So that's how much ever change in momentum happened and how much time it happened. Now time here is critical. So we are the way we understand time here is we won't on an average, like what happens is this particle changes this much momentum every time it collides, right? So the time between collisions for to go from here to here and then back, right, is the second collision time. So what we want this time to be is this time needs to be the time to travel between collisions. So this is time between collisions. So time between collisions is, so this is like t by 2 and this is t by 2 in a way. So what is t by 2? Is like distance is traveling in constant speed. So the length is distance upon velocity. So distance is L that you want to translate. Maybe the one, this is a say cube, all side lengths are L. So this is L this is L, and this is L. So it is distance by velocity. Velocity is already assumed that it's traveling at v. So this time between collision become 2L by v. So this is the time between collision to collision. So then this becomes minus 2mv by 2L by v, right? And then you cancel these out, and then you get minus mv square. So that is something, that is the force that is being exerted by the particle, by the wall on the particle. Okay, then next thing we need to know is also on the wall by the particle and on the particle by the wall. So both, like, because Newton's third law, right? Okay, now next we want to know what is the pressure exerted by these particles on the wall. So that's how much our force that was needed to be exerted by area, right? So minus half mv square by area of this full surface is L square. So L cross L, it's a square. So it becomes like something like this. Oh, there is a divided by L that's missing. So it becomes divided by L cube. So now we have like some kind of a basis. So this formula minus this we have. So we start to think about this a little bit more. Okay. So let me bring this to the next page. So what we have found till now is pressure is equal to mv square by L cube with the minus sign. Minus sign doesn't matter. Minus sign is only thing about indicating what is the change in momentum. That's okay. It doesn't really matter to us. So maybe we can just get rid of minus n right now, right away. Okay. Okay. Uh, Now what we start to see is okay. Let me just refer your book for something. Yeah. So okay. So this is for one particle, right? Now say you have say n particles. Like now they're not just one particles, but all of these n particles who are now moving in different directions. In that case, your pressure will definitely be more, right? N times this number. But instead of v square here, what we want to mention is a different kind of a term, which we replace with something that looks like this. Now the question is, what is this? So this thing, we can say, is kind of like the average velocity. Um, so this, in this case, in the first case, we are just assuming that a particle is going left, then going right in a way. It's like one dimensional, right? But in a 3D space, it can go anywhere, right? So what you would just want is change of momentum in the x direction only. So kind of like this is like Vx, right? So we can say that the total velocity V square is divided. This is always true. Like Vx square plus Vy square plus Vz square. It's like how you say ki, okay, what is the what is the length of this vector r will be equal to x square plus y square. But if say this is in 3D space and say there is a z square also, something like this. So the vector will go from this point to this point, something like this. So the magnitude of this vector, if you think about it, and if this is z, then it will become here in this case r. So r square will become x square plus y square, which is the normal this thing. But then you also have to lift it out of the plane here in this way. So plus z square. So this is something that's always true. Now because Vx, Vy, Vz all should be same. So this becomes V square is Vx square uh, whole by 3. So what we ultimately get is whatever this is the mean velocity by magnitude. So this by 3 is kind of like R uh, V square. Okay. So this is a little bit complicated. Try to rewind the video and try to see what we are trying to do. So this is just a magnitude of any vector that we have, right? X square plus y square plus z square. In this case, x and y and z, all the terms are same. Vx, vy, vz are all same. So once we put that into this formula, we get vx square by v square by 3. So and then okay, so we get v square by 3, but what are these symbols? So this is just like an average velocity, because all of the particles are moving at different velocity. We just want to say what is like the average speed of all the particles. So this symbol means the average. Okay. Uh, so okay, we are getting somewhere. So now we have accounted for all the particles and particles, and then we say that okay, maybe let me try to manipulate this a little bit. Try to add so this L cube here. So L cube, if you think about it, L square we said was the area of one side. So L cube is L length breadth height. It is like the volume. So I can simply say that L cube is the volume. I'm taking it to the other side. So this becomes 1 by 3. So let me also take this. Mhm. And then what is left is Mn, this and this average velocity term. Uh, okay, let me just cross check whether we are on the right track here. Yeah. Okay. So this is the okay. So we have gotten till this point. So one another form that your book gives is if we can write the same formula here by as this, right? So this n by v term is number of particles per volume. So that's the kind of like the density of the particles uh, into a mass of every particle into c square. So this is also a formula for the pressure of a gas. Okay. All of these kind of you don't need to like strictly remember, but oh, nm, sorry. So m will also be gone because the part num n m is the mass of all the particles. Uh, nm is the mass of all the particles, and mass by volume is density. So then this will also disappear. Right. Okay. So we can say that the pressure of the gas depends on only two things, which is kind of like the density of the gas and the speed at which the particles are moving, like the average speed of the particles. So this is what the pressure of the gas depends on. So this is one of the things that we can like understand from our this thing. So let's continue from there. Okay. So a few observations. Let's look at this equation a little bit closely, because these things can uh, be a little bit tricky. So let's check whether what we have said is correct or not. So it's saying that when volume is high, so first thing, when volume is high, then pressure is low, right? Because when the denominator is high, this whole term will be dragged down, and then this will be low, right? So this is exactly what Boyle's law is, right? So we can understand through kinetic theory that we can say that when volume is lesser, the same amount of particles now will hit less in less time, right? They have to travel that 2L by c distance to hit again. Now if L is larger, then they will hit in lesser time, so the pressure will be lower. So this guarantees our Boyle's law, right? Another thing is it's saying that if the velocity is higher, uh, then the pressure would be higher, right? So this makes sense if the particles are moving faster. So if temperature is higher, then the velocity is higher. If the velocity is higher, then the pressure is higher. So this makes sense, right? Because a higher speed particle will cause more damage. And similarly, when the mass is higher, then also the pressure. Let me try to do it with a different color. So when mass is higher, then also the pressure is higher. So if you have say bigger particles, uh, then they kind of tend to have a higher impact on pressure, right? So all of these observations kind of tell us that we are on the right track. Our equation seems right, and it has these characteristics which make sense. So you can read the book for a higher clarity here, but this is the section that talks about exactly this. Okay, if you understand this, let's move on. So the last thing is now, if we have if you have found this equation, right? So this is PV equal to let's write that equation again. PV equal to 1/3 number of particles into m into c square. So we know that okay, this is what kinetic theory gives us, but we also know that this must be equal to nRT, right? Where n here is the number of moles and r is the gas constant. From this is the ideal gas equation. So now we try to make some comparisons. We try to see. Uh, so we try to look at this part now, and we are trying to see. So number of moles is always equal to n by Avogadro's number, right? So this is the number of particles. This is a fixed constant, the Avogadro's constant, and then this is the number of moles, right? So here we see this term, this n by n term can come. So I'm rearranging this stuff here. So it becomes mc square is equal to n by n into RT. So this n by n will become 1 by Na RT. Then one more manipulation that I do is I add a half here. So 3 I take to the other side. So it becomes 3RT. But because I divided by half, I need to divide by half here again. So something like this, right? So let me just write this like this. Now another thing I say is, okay, this R by N, these are both constants. So R is the gas constant and N is the Avogadro's constant. So I make them one constant, which I call the Boltzmann constant. So this is where the Boltzmann constant comes from. So this becomes K. K is equal to R by Na. Okay. Now if you understand this, then what do we have here? Let's see. So let me take it to the other slide. So we say 1 by 2 mc square is 3 by 2 kt. So this 1 by 2 half mc square looks a lot like what we can say as the average because of this term, average kinetic energy of all the particles in the gas. That is equal to 3 by 2 kt. So this is a very important kind of conclusion. So this from directly from like first principles, directly from these calculations, directly from this kinetic theory, we are understanding that when the temperature is higher, then the kinetic energy will be higher. So this is why I always say, or we always understand that temperature is a direct uh, measurement of the average kinetic energy. Except the only thing is there is a conversion factor because this is a temperature in Celsius and this in Joule or Kelvin and Joule. So we multiply a Boltzmann constant here. So Boltzmann constant is kind of like converting you can say like a macroscopic quantity to a microscopic, which is related to the particles, right? Kinetic energy is a particle and for of a particle, but temperature, pressure, volume are macroscopic. So Boltzmann constant is kind of like a conversion. So units will be joule per Kelvin, right? So it is kind of converting directly from 1 Kelvin to 1 joule. How much is the energy that's translating, right? And this has some value like 1.38 into 10 power minus 22 joules per Kelvin, but that's not very important, right? So there's another factor 3 by 2 also in front. So it's always good to remember kinetic energy as three halves kT, as your book says. Like it's just like mnemonic. Good thing to remember. Okay, we are almost done with the chapter. Uh, we'll just see. So there are okay. So there are two sub points that your book mentions. So one thing is instead of saying average kinetic energy is proportional to temperature, it says mean translational kinetic energy is proportional to temperature. So your book wants you to understand what is translation kinetic energy and what is mean. Why are these two terms we are referring to? So translational energy is, so your book gives this example here, which is pretty nice. Uh, so it talks about if there is a single monoatomic particle monatomic particle. So it's not like O2, it's like neon maybe, which is just a particle. But and on the other hand, your diatomic particles. So when these two molecules are kind of stuck, atoms are stuck to each other, so they can also rotate. So they have rotational freedom also. But if there is just one particle, then it can just move. But a diatomic particle can kind of rotate and move at the same time, right? So it has both translational and rotational freedom, rotational kinetic energy. But what we are talking about here, this is equal to 3 halves kT. This is only accounting for the translational kinetic energy, first of all. So there is no concept of rotational right now. What do we do with rotational? It is not we are not going to study it now, but it's important in other context. Okay, so that's one thing. And the other thing it wants you to understand is the mean. So mean is basically kind of like saying that okay, you have one particle and that kind of at every collision it changes speed. So you can just observe that particle for a long time and see all of the velocities that it has and then kind of average it out. That's one way. Or the other way is to say that all of the particles at one time have some velocity. So you can just take okay, particle 1 has this velocity, particle 2 has this velocity, particle 3 has this much, and then you can average it out. So one way is to say that one particle at all times has different velocity, so you average them out over time. But one and the other one, you just say that this time all of these particles have this much velocity, uh, so I can just average them out right now. Both of them give the same answer, so that is what is meant by mean here. So that's how the process of taking a mean works. Okay, so that's one. And the last subtle thing that your thing is talking about, book is talking about, is this idea of this what we call the root mean square speed. So let's understand what means by that, or like what we were till now calling average speed. So so if there are say three so your book gives an example here. So let's follow the book's example. So it says that say there are three particles with speeds 10, 20, 30. Okay, so their mean speed obviously becomes 10 plus 20 plus 30 by 3. So that's 20. Now their mean square speeds, right? So you square all of them. So square speeds are 10, 10 square, 400, 20 square, which is 400, and 300, 30 square, which is 900. So mean square speed is the mean of the square speed. So you take all the squares and then you mean them. So you get 467 and then you square root it. Right. So root mean square. Right. So first you squared, then you found this mean of all the squares and then you're square rooting it. And that answer you get as 22. Right, and you see that root mean square is not the same as just the mean speed. So which is why like that's one subtlety that it mentions your book. So it talks about how mean speed can be 20, mean square is something like 467 or whatever, and then root mean square is 22. And what it tries to tell you is that this is not equal to your mean speed, which was the original thing. So in the all our formulas, we are talking about this root mean square or this RMS speed, root mean square speed. So just be careful about this little speed. So this is mean speed. So this is root mean square. So there are like three things there. So just a small subtle point, but you should know it. Okay, and very last point that it mentions is so very small point that we know now that kinetic energy or mean translational kinetic energy is 3 halves kT, right? So that means that if we increase the temperature, uh, that if at a particular temperature, uh, all the gases, so say consider air, right? Air at say room temperature at 27 degrees centigrade. So it is composed of different molecules, right? So it has nitrogen, it has oxygen, it has carbon dioxide. And if you calculate molar masses here, then this becomes 28, this becomes 32, this becomes 44. You can calculate them. Make sure you know how these numbers are coming. These are molar masses, right? So you see that everyone has different mass, but because of this formula, at same if this is same, then kinetic energy is same. So kinetic energy we know has two components, right? So it has a mass component and a velocity component, this root mean square component. So because the mass here is high, so speed of all these particles is slow. So these are fast, this is in the medium, and then this is kind of slow. So, so if you imagine all of these gas particles at room temperature, so some are moving very, very fast, like smaller molecules like hydrogen are moving very, very fast, nitrogen is moving very fast. But these heavier molecules tend to move very slowly because of this problem. All of them need to have the same kinetic energy, but some have higher mass, so they need to have lower speeds, right? Okay. So this is good. Just finish all the examples and the solve the examples as we discussed last time, and all the internal questions that this has. You can upload it on the link. I'll just check it when I have the time. Okay. Have a good day. Bye bye.